Hey, welcome back to an exciting presentation on vectors. It's called Applications, and we're going to put together everything that we did with the equation of the line and see if we can make some use of it. And I've invited the pilot of this plane to have a look at this, to adjust his flight vector, flying in all other weather there, mate. And these two certainly need some help, so they're going to have a look at this video as well, see how they can get the path there, the direction vector of their boats, so they don't collide now. Okay, so that's the idea, and down here you'll get an idea of how we're going to do it. You do need to insert some sort of a grid system. With the way we've developed our equation of the line, we still do need a grid system. This might be a 2D system in the case of boats. We set sail from A in a particular direction with a particular velocity. Somebody else sets sail from P, and we want to meet at a point, don't we? What are the coordinates of that point are? That sort of thing. And over here with the planes, it would have to be what? A 3D system, wouldn't it? It might be north and south, east and west. Usually we use east and west as the x. And here, in the z direction, would be the altitude of the plane, perhaps. So all of this does require the positioning of an appropriate grid system, so we can go on with the equation of the lines that we had before. All right, come on down and let's look at the ideas now. These are constant velocity problems. Screen clippings used in this presentation come from Hayes and Paris publications and also Pearson's. So we're going to change. Here's our equation of our line. We're going to say to get to any point on the flight path, we start with going out from the origin, our setup, our grid setup, and then if t means time, this is a big thing now. If t means time, we've got that many lots of the velocity vector, b. And then you could call it little v. And so every second that goes past, then you'll go so many metres in the x, the y and the z if it was 3 dimensions. Over here, let's look at the picture. You're travelling out to A, this is the idea of the equation of a line, and then you've got t lots of the direction vector. And if this is velocity, then the t lots is special. It's time, because the movement, the displacement, will equal the distance times time. Okay, I did it wrong there. The distance is velocity times time, sorry. Velocity times time. Okay, that's what we're going to do. Can you see? We're working it around our mathematics here for the equation of a straight line in vector land to something very useful. Let's go down and have a look at that happening. Okay, so here it is in 2 dimensions. Okay, so we're setting off in the direction 220. So what could that mean? That could mean in the direction 2 kilometres north, and what was it? And the y? Oh no, we usually take 2 kilometres east and 20 kilometres north. We usually do let this be north and east in 2 dimensions. So we could say something like that, and then we've got a velocity vector here. Let's say it's 4 metres per second in the x and -3 metres per second in the y. So what that means is from point A, when we get there, every second that goes by, we're going to go across 4 and down 3. So I think we've drawn the picture here of just one lot of that velocity vector. That's a second later than when we were at this point. So here it is over here. Come back over here. If t is 1 second, and this is the velocity vector, we get this picture. 220 has gone 4 in the x, maybe this would be 6 now, and down to 17. Okay, get the idea. The velocity times time is going to give us the displacement in both directions. This is handy. Let's get excited and see how we can apply it. And here's the first example from Hayes and Harris publications here. So, oops, lost it again there. We'll just come back up. So here we go. We're going to try and interpret this as a vector equation of the path of an object. So we're going to come along and we're going to use this as the velocity and this is time. Okay, find the object's initial position. That's when t is 0. And that's just going to be going out to that starting point there. 1, 9. See it over here. Okay, velocity vector is 3, neg 4. Okay, so what we would usually say now, this is east. East-west is the x, so this is positive, so it's east. And this is north-south. And so it's negative, so it's going negative y. That will be south. Let's draw it. So in the first movement for t is 1. It's gone across another 3 across here. And then down 4. So instead of 1, 9, it's up 4 and take away 4 from 9. It's 5. Get the idea now. Each time unit that passes, the effect on our position is going to be 3 more in the x, 3 more in the east, and neg 4 in the y, which means 4 units south. Hey, this is interesting. And what would the speed be? Well, if this is the velocity vector, speed is the size of the velocity, so it's the size of that vector. Pythagorean triple here, 5 metres per second. Okay, just remembering a little girl over here reminding us velocity is a vector, so it's got an x and y component which will give us some idea of the direction, but speed is a scalar, it's just a number here. Okay, so the new velocity vector is what? Now, the speed was 5 metres per second when it was like that. The new velocity is, well, it says here, it increases its speed to 30 metres per second. Sorry, I didn't read that. So that's a velocity vector with 6 times the magnitude. So 6 times 5. So the new velocity vector is that. Okay. So do you get the idea? Unit vector is going to come into this bit. I think later on, if we want to construct a velocity vector of a certain size. But here we can simply say, come up the top again. This is 6 times 5, so it equals 6 times the original velocity vector. And so that's where this comes from here. Get the idea. We have to move it across to a context now. So this is an exciting application of all the work we've done in vectors. Okay, let's do it again. A vector, object is initially, this could be a boat, with a velocity vector of 3 neg 1 metres per minute. Okay, position of the object at time t minutes. Well, there's our original position, x, y equals 5, 10, and every minute that goes by will have this many lots of metres per minute in the x direction and the y direction. Okay, so after t minutes, what's its position? Let's use the parametric equations. 5 has had, what? T minutes worth of 3 metres per minute in the x, so it's 5 plus 3t. The y value was at 10. It's had t lots of neg 1 movement in the y, which is 10 take t. So after t minutes, the object is at 5 plus 3t, 10 take t. Get the idea. So parametric equations can be used to represent the position of the object after t minutes. And here's our drawing here. We travelled out to 5, 10, so this was the vector 5, 10 to get out to that point. And then we're going to have t lots of this thing here, 3 neg 1, which is b, which here in this context is our velocity vector. Good stuff. And the speed of the object is the size of that b, which is the root of 3 squared plus neg 1 squared, root 10 minutes per metre. Okay, after 3 minutes, we will have 3 lots. Come over here, I think. This will be 3 minutes. We'll have 3 lots of this displacement in the x, this displacement in the y. So it'll be 5 plus 3t is 14 and 10 take t. Okay, so that will be the idea after 3 minutes. So the object will be at 14 and 7. So 3 is in here, t is 3 after 3 minutes. So you adjust the displacement accordingly. So the time when the object is due east of 0, 0. What is due east? Well, that means in the the y direction, you haven't travelled north or south. So you want here, the due east of that will be some x coordinate, but y must be 0. So let's take the y value up here from the general position in parametric form of the point in the y direction. So at t is 10. After 10 minutes, it will be due east. We don't care what the x is, how far it's east, but what we're focusing on is that the y value will be 0, because y value is the north or south component. Okay, getting the idea of it, we're gearing up here to do a good application across to motion problems. So here's some from Pearson's then. We've got a plane of an appropriately fitted coordinate system, such as position is this. So there's no height here. Now these should be, in this syllabus, column vectors, explicitly mentioned in the syllabus. Please write your vectors as column vectors, column vector there. Where t stands for time in hours and the start and distance are measured in kilometres. Okay, very good. Find the initial position when t is 0. Down here, the point is 3, 1, because you haven't moved anywhere with that velocity vector yet. Show the position of the object on a graph at start, 1 hour and 3 hours. So let's have a look and find the velocity and speed of the object. So where is it at the start? It's the point 3, 1. It's down here, 3, 1 on our system. Okay, and then 1 hour later, where's it gone? It's gone one lot of -2, 3, which is our velocity vector. So it's across at 1, that's been moved -2, so it's gone west, and then 3 in the y, so 3 would be north. So it's gone to the point 1/4. And it's going to keep doing that because it's a constant velocity problem. So the next hour, it's going to go across -2 and up 3. So where's that now? -2 and up 3. This is 0.14. -2 will be across here, and up 3 will be 7. So here we're going to go across 3 and up 1. What have we got? We haven't done that. Let's have a look. Let's just check this addition here. -2, 3 every time. So 1 take 2 is -1. Now we've just got to check the scale here. Yep. So here we're going across -2, so the scale is 2. We're across here and we've gone up 3. So 3 added to 4 will be there. So that's our next hour of motion. Okay. -2 means going to this way, to the west, and then +3 will be going up to the north, and we're there. Then if we do it again, scale here just confused me there for a minute, is 2 squared is 1, so that's a -2, 3 shift again. Okay, can you see with constant velocity problems, each time unit, if t increases by 1, you will move the same amount from before in the x and the y. Okay, and what's the velocity? What's the speed going to be? The speed will be the size of the velocity. So the speed is the size of the velocity, which is the size of the vector -2, 3. Okay, and again, using what we did before based on Pythagoras, the size of that is root 13. Okay. So we could say it is root 13 in the direction of -2, 3. Okay. And what we could do is put it this way, as a unit vector type thing, or we could quote its direction as theta is tan -1, or 3 over -2, that from before, or cos -1 of -2 over root 13. Just remember now, that's the angle with the x-axis. This is our vector -2, 3. It shouldn't be poking out that way, but anyway. This would be the X and the Y here, and we should put it in the other quadrant. Oh, I better put it in the other quadrant to make more sense here, but we're using rules from before, so it's -3 out there, so this angle, we work out our cosines and so on, is going to be a negative here and 3 here, so you could work with the tan of this angle, 3 over -2, or the cos, which is -2 over this length, which is √13. So know your little bit of maths there for that angle, because you can use either the cos of the x value over the length or the tan of y value on x value. Okay, building up some ideas here. Let's look at a 3D problem. Okay, 12 midday, a plane A is passing in the vicinity of an airport at a height of 12 kilometres and a speed of 800. Direction of the plane is 43 north. Okay, so we're going to set up a grid system. 1 north is placement of 1 kilometre due east, yep, and 0 1 north is due north, 1 for the y, and 0 1 is an altitude of 1 kilometre. Using the airport as the origin, find the position vector of the plane t hours after midday, and 1 hour after midday, and then look for another plane. Okay, so we'll come back and look at that other plane in a minute. Let's do the first thing. Position vector at midday is 0 0 12. So that means our position vector is 0 0 12, and every hour that goes by, how far are we going to displace our plane? Well, hang on, the direction is 43 north. So we could say, as a unit vector, that is 1 over 5, because the size of this vector is 5, Pythagorean triple, so unit vector is 1/5. So the velocity vector, it's 800 lots of that. Now there's a use for our unit vectors. So this is how fast it's changing direction, east and west, x and y, north and south here. So it's 0 0 12 plus that, and they should all be as column vectors like this. Okay, don't forget to adjust that direction vector to a velocity vector by multiplying by, here it is here, the actual velocity you require. So that means you've got to reduce the direction vector back to a 1 unit vector and then multiply it up to 800 kilometres an hour. Bit tricky there. Okay, after midday, 1 hour after midday, t is 1 in there. So it's gone 1 hour's worth of this velocity vector. So it's still at the same height, but it's now gone further east and here further north. Now, another plane, let's go back up here. Another plane has got this velocity vector. And it's starting to locate, its location at the start is that. So it's also, notice this, 12 kilometres above the ground, and that part of the velocity is not changing. In other words, it's travelling at an altitude of 12 kilometres with no change with that height in its velocity vector. It's going to stay at 12. So let's have a look at its position vector. R is its position now, which should be 600, 480 and 12. And every hour it's going to move -300, -400 and 0. So what's going to move? It's going to be moving west and then south and constant altitude. So look out, it could crash with the other plane because that also was moving at a constant altitude of 12 kilometres. So will the planes ever crash? So put the position vectors equal to each other. We should have called these R1 and R2. This was the first plane. Here could have called that R1. This is the second plane. You might say, well, Huddy, hang on, don't we have to have different parameters there? Because they're different bodies. No, you don't. Why? Because the parameter is common. It's time. Because the way in which the flight paths are going to extend is the velocity vector times time, and the planes will experience the same time frame. So these remain the same value parameter in this application. Okay, so if you try to do this, what do you get out of it? We're going to use parametric equations again. So we can say 640 times T1. Here, two parts of the main sec. They put in T1 and T2. All right, because it could be travelling different distances. Yep. All right. So we're trying to find T1 and T2. Are they the same? So here we want what? 600. Here, let's do the x's. 600 take 300 by T2 has to equal 0 plus 640T. And then do the y's. 480 take 400 T2 has to equal 0 plus T1 times 480. So, they are those two equations. If we solve them, we get 12 equals 12. Okay, so what does that mean? Okay, solving the system will give T1 is 6 over 7, T2 is 6 over 35. So you're trying to find a value so that those two are both going to be equal. Okay, the 12 equals 12, other two altitudes will remain the same because they're at constant altitude. So we've got 2 times here, solving them. We're at 6/7 for plane 1 and 6/35. So they will cross at a common point. They're both coming at that altitude, but it's at different times. 6/7 of an hour after midday and 6/35. If you work that out, it's 12:51 and 12:10. About a half an hour difference. Did you get the idea? So T is common, T means time, but we're looking to see at what different times the position vectors, the x's and y's at that point, are the same. Alright, let's go down and have a look at doing some. So here's some from Pearson's. We've got just the usual application here, cars in 2 dimensions. Yep, right through 10, 11 and 12. 3-dimension problem in 13, not really an application. And then a 3-dimensional problem in 14, which is not really an application. It's only a geometry problem. And then we've got similarly in 15. Okay, I'm going to give you some others in a minute from Hayes and Harris, which are more in the applied vein. So let's have a look at the solutions to these down below here. So there's 10. Let's have a look at 11. Oops, gone too far here, just coming back, sorry about that. There's 11. And then 12. 13. And 14. Rest of 14 there. 15. Okay. Let's move on to more motion application problems. So here we are, exercise 13 from Hayes and Harris publications, similar to the ones we saw above. So have a go at those 3. Let's now have a look at the others. I don't think we can get them all on. 4, 5, 6 and 7. Okay. And 8. Okay. This is a good problem, submarine problem here. Okay, finding when the torpedo might actually, 2 torpedoes might knock each other out. So have a go at that one. I'll put the answers up now. verse 4. Rest of question 4. Okay, 7 and 8. So we've got some stuff going on there, and it's exciting. I mean, the best applications that I can think of are the motion problems, but the ones involving triangles and stuff are interesting too. All right, look, there's one more presentation where I'm going to produce Pearson's practice questions and their solutions. So we've done all the theory now. It is only a matter of getting in and doing some practice. So good luck with that. Cheers for now. I'll catch you in that final presentation.